Hi, everybody. This is Stephen Hansen, and I will be meeting all of you soon in a couple of weeks in Madrid for the Machine Learning for Textual and Unstructured Data course at IESE. And I'm very much looking forward to introducing myself in person. But because during the week we will have somewhat limited lecture time, I agreed with Stefano, who's been helping organize the course, that I would do a couple of pre-sessional lectures of background material that may be helpful preparation for the main lectures. So I have to admit, this is the first time that I've recorded lectures in advance. So we'll see how this goes. What I'm doing is sharing a slide deck via my iPad here on a Zoom call in my office in London. And I'm going to go through these slides and discuss their content, and also occasionally, I think, if I need to, flick back to just a kind of a whiteboard that I will mark up. And I will ask Stefano to distribute, along with this video recording, the lecture slides that I'm going through now, in addition to any annotated whiteboards that I make over the next hour. So we'll see how this goes, and I hope that it is useful and that my kids don't run into the office in the middle of this recording. So let's go. All right, so there are a few ways of modeling and quantifying unstructured data, as we'll discuss extensively when we see each other in Madrid. But one of the ways that one can begin to model unstructured data is with a statistical model, where we write down a data generating process for our unstructured data and infer the parameters of that data generating process using some inference procedure. So basically, this set of lecture slides is about specifying a model of high dimensional count data, and I am going to use textual data as a motivator for this model, although, as we'll discuss, this model can also apply, or variants of this model can also apply to other kinds of unstructured data. And I want to discuss two alternative ways of doing inference in this simple model. So the first is a classical kind of maximum likelihood based approach for parameter inference, and another is a Bayesian approach to inference. And I will discuss the advantages of using a Bayesian approach in this setting when the number of parameters becomes high dimensional. All right, but before we begin these lecture slides, you already see that there's a bit of annotation in this first slide. Maybe it would be useful to step back and just give a simple example of what I mean by a textual database. And again, we're gonna spend much more time talking about this in Madrid. But let me just begin by saying what I have in mind is a list of words. All right, so I guess I can start writing on this. So good morning. It is nice to meet you, at least virtually. Okay. Now, the first step in representing this string or this sequence of text is just to break it down into its individual elements. And I can start thinking about this as a list of elements. So good morning. It is nice to meet you. All right, so now I have a list of elements. And the way you go from the raw string to the list of elements is sometimes called pre-processing. We're not going to talk about that right now, but let me just say that our starting point for this lecture is the idea that you have a sequence of words, okay? And each one of those words has been mapped into some index, all right? So it doesn't really matter. We can call this good is 1, morning is 2, it is 3, is 4, nice is 5, 2 is 6, meet is 7, and you is 8. Okay, so we have 8 distinct words in this in this list, and each one has been mapped into some unique integer. Okay. So once I have this mapping from words to integers, I can start building new texts using these same 8 elements, right? So if I were to now generate for you the list, sorry, zoom back out. So let's say, if I started saying 1, 3, 5, 7, 4, okay, this might be a little bit nonsensical, but I can still start defining other word lists in terms of these integers. All right, so this 1, 3, 4, 7, 4 would be understood to create the word list good, it, is, meet, is. Okay, and so on and so on. All right, so we want to start writing down a statistical model for producing any given sequence of text. Right? And the way I'm going to start building this, you can think of it as a model of a coin toss. All right, so when we think about a normal coin toss, there's a tail side of a coin and a head side of a coin, and I just start flipping it. Right? And that generates a sequence of 1s and 0s, where you can think of 0s as heads and 1s as tails. Okay. So if I have a 2-sided coin and I flip it, that is going to be a data generating process for creating a 0 or a 1. Right? There are binary outcomes, and that's how I can kind of think about generating that. Well, in this, in a textual database, we have more than 2 possible outcomes. Right? So the number of possible outcomes that I have, at least in this simple setting that I've just written down on this whiteboard, is I have 8 possible outcomes. Right? So every time I generate a word in a list, there are one of 8 possibilities that might come up. So I could either generate good or morning or it or is or nice or to or meet or you. That's the assumption. Right? And every word in my list is going to be independently generated. So in this very simple text model, which will relax at various points in our course, but in this very simple first text model, every word in my list is going to be generated independently. Okay? So I'm going to go to, let's say I need to fill in, in slots of a list. So how am I going to fill this first slot? So which word is going to appear in this first slot? Well, I'm effectively going to take an 8-sided coin, not a 2-sided coin, and flip it. And there's going to be some probability that that 8-sided coin lands 1, some probability that it lands 2, some probability it lands 3, and so on. Right? So I'm going to have 8 different probabilities of my 8-sided coin. And to generate this first word, I'm going to flip that 8-sided coin, and it's going to land on one of its sides, and the side that it lands on is going to generate this first element, okay, which might be whatever, 2. And then I'm going to repeat that process for this second slot. And my coin toss for generating the second slot is going to use the same, it's going to be the same coin. So the probability of side 1, side 2, side 3, all the way to side 8 is the same as the coin that I flipped to generate the first slot, but it's going to be an independent flip. So the fact that the first slot showed up 2 is not going to affect the probability distribution over this second slot. Okay. Same for the third slot. Same for every slot until I populate my full list. So I'm basically going to take in different throws, where in is going to be the length of the list. Okay. So I'm going to take my 8-sided coin and flip it capital N times, and I'm just going to record the side that the coin fell on for each of these in flips, and that's gonna generate me this list here. Okay. So that is essentially a complete, it's a complete description of a data generating process for text. We can object to various aspects of the model because it's a very simple model, but at least it's a starting point for writing down some data generating process. And now we need to formalize a little bit what that data generating process is. And that's what the main slides do. But if you get this basic idea of tossing let me make it a bit more general in notation. So we have capital V possible words that can populate our list. Okay, so we can move a little bit away from this idea of these 8 specific words that we had in this whiteboard and think more generally about capital V possible words. Then what I'm doing is writing down a data generating process for how these capital V possible words appear in this list. Okay. Well, so the first thing I need to do is describe the structure of this coin, all right, because it's the key thing generating these probabilities. So the way I'm going to do that is write down a sequence of probabilities. I'm going to call them beta 1, beta 2, all the way through to beta V. Okay, and that's a probability vector. All right, so what do I mean by that? I mean that every element lies between 0 and 1. Oh, sorry. Okay, so every individual element of that probability vector lies between 0 and 1. And if I sum over them, I'm going to get 1. Okay, so that's the definition of what it means to be a probability vector. And these individual beta V's describe the probability of term V showing up in any given slot, right? It's the probability that the V side of the coin is seen after I flip it. Okay, so let me just write that in English. So beta V is the probability of seeing, it's a bit informal, so I'll put that in quotations, of seeing term V, which I'm going to assume is somewhere, right? It's either 1, 2, 3, 4, 5, 6, all the way up to capital V in my list, okay? In any given slot in my word list. Good. Okay. So that's basically the parameters of the statistical model that I need to infer. Okay, so that's the, depending on whether we're doing frequentist or Bayesian estimation, we might think of these things as parameters or random variables or whatever, but we'll get into that in a minute. The point is these betas are what we need to learn, or they're what we need to estimate. Okay. So with that background, let's jump back into our lecture slides. And I think that we've basically covered most of this. So let me see if this laser thing works. Great. All right. So that what I was just describing basically covers these first 2 bullet points. And all right. So one more bit of notation is that I'm basically going to take my word list, right? So this, this sequence of words, and I can describe that word list as just a vector of counts. Okay, so I'm gonna collapse the original word list into a count vector. So just so we're totally clear on what I mean by that. So let me take again this list here, which we wrote down at some point. All right, so I'm going to copy this and let me pull it down to a new place. Great, okay. So I had this, I had this word list, good, it, is, meet, is, that was codified by the integers 1, 3, 4, 7, 4. And what do I mean that I can collapse this down into a count vector? Well, I'm gonna think about there being a count. So the count, right, count of term 1, count of term 2, and so on and so on. And in this particular case, there were 8 possible terms. So this would go all the way out to count of term 8. Okay. So this count vector, X, is just going to collect all of these counts. So what's the count of term 1 in this list? It's 1. What's the count of term 2 in this list? It's 0. What's the count of term 3? 1. What's the count of term 4? 2. What's the count of term 5? 0. Count of term 6, 0. Count of term 7, 1. Count of term 8, 0. Okay. So any given word list, which is a sequence of integers, I can convert it into just this, counts. Now, under the assumption that every slot of this list, right, so this 1, this 3, this 4, this 7, this 4, under the assumption that every slot was generated independently, there is in fact no difference between recording the counts of words and the sequence of individual realizations, right? Because the sequential information of these words is not actually relevant to their data generating process, right? And so all I'm really doing is creating a statistical model for the number of times word 1, word 2, word 3 appears in a list, right? So I guess another way of stating that is that the underlying probability of this list would be the same as the underlying probability of this list. So 7, 4, 4, 3, and 1, right? That list has exactly the same counts over terms as the first list. Of course, the actual underlying language is different, right? So the sequence of words is different, but the count of the number of features or terms in each of these vectors is the same. And so because those were generated independently, their underlying probability is the same. So really all I need to do is model these count vectors. Okay, so that's what we're doing in the lecture slides. And by the way, there's a little bit of a typo here. This should not be X. This should be W. Okay, and then X is this vector of counts which I just described. Okay. All right, now all of this can be summarized with something called the multinomial distribution. So some of you who maybe have studied some basic statistics may know what a binomial model is. So a binomial model describes the distribution of the number of ones in a sequence of coin tosses where we have, zeros and ones representing heads and tails. The multinomial is the multivariate generalization of a binomial distribution. So when I flip a V-sided coin in times, it describes the distribution of the counts over the 1s and the 2s and the 3s and the 4s and all the way up to capital V's, right? So in summary, our statistical model of text is a multinomial distribution where the parameters of the distribution are these beta terms, which describe the probabilities of seeing the features in any given slot. All right, so that is a basic model of count data, where I've given the particular motivation of text. And now we want to do inference on these beta parameters given the data that I have in front of me. All right, so because this is the first time I have done one of these recorded lectures, I'm actually going to pause now, stop the video. If everything looks good, I'm going to rejoin you and carry on with the rest of these lecture slides once I verify that this little test has worked well. So I will see you soon.